The objective of our heat transfer project was to find out how the heat dissipation of the airflow happens within a rocket stove. So Kai McCord and I, Josh Young, will be doing this project and helping you understand what we found out. Rocket stoves have been designed, have a designated inlet for fuel and air and an outlet for the exhaust gases and heat to escape where cooking is performed. This setup is to allow for more efficient and complete combustion of the fuel while concentrating heat to the cooking surface. While operating, an ideal rocket stove will produce a low wind sound due to the increased velocity of the heat exhaust gases escaping from the outlet, hence the term rocket stove. A typical rocket stove is square or circular in shape. The type of rocket stove that we have decided to test out was a triangular model that was meant to be collapsible, shown in the right figure. Determining the heat dissipation requires a comparison between a prototype and a model within a computational fluid dynamics program. In order to get a good idea of how heat dissipation really is for our model, we needed to use a numerical model just because we saw some foreseeable hindrances with our measuring devices. But we'll get to that in a minute. As mentioned above, we're using a triangular rocket stove. We're only going to model having an inlet and an outlet. But we do understand that there are some gaps along the sides as it goes up because it is collapsible. But we're going to neglect it to simplify our project just a little bit. In the computational fluid dynamics CFD model, we decided to go with an ambient temperature of 300 Kelvin. The fire itself will be around 1,000 Kelvin because the average fire burns about around that as well. Just so for your information, the boundary conditions, we did not know how the inlet would act, if it would actually push some of the hot air out or in. So we decided to kind of leave that up to as a zero gradient there. But the walls itself, we knew for a fact they wouldn't change very much, so we left them kind of as a zero gradient as well. Stove temperatures were measured in our, as you can see in the images. We lit the stove and tested it as our prototype, and we did find out using an infrared thermometer that it was very hard to get an accurate statement or accurate temperature. Data from this experiment provided to be inaccurate and was eventually thrown out. Due to this inability to measure the prototype with great uncertainty, it led to this testing of boiling water, which we used for 2 cups of water with the initial temperature of the water being 10 degrees Celsius. Began boiling 9 minutes with a final temperature of 96 degrees Celsius. It was calculated approximately 305 watts would need to boil the water for that time limit. For this, now onto the CFD model. Now we only modeled, this is a slice of that model, and so you can see this is the final representation of what happened with the velocity. And you notice that as the velocity, as we move further down towards the outlet, which is on your left, you see that the velocity actually does increase, but it increases as it gets farther away from the inlet as well, where we see the greatest velocity, which is 0.74 meters per second, down towards the bottom. This actually corresponds to the temperature and how the temperature is weighed. You can't really see it. You see it's a little bit lighter shade of blue on the left in that picture, but you can really see it here. We just took a graph and graphed it from the base, which is at 1,000 degrees Celsius, or 1,000 Kelvin, clear over to the outlet. It does decrease quite quickly, but it does stay over 300 Kelvin, which is nice because that 300 Kelvin again is our ambient temperature. At first glance, this data didn't really make sense to us what we were seeing, because we saw our greatest, at the greatest point of our velocity, the temperature coming out was about 360 Kelvin. And so we were a little bit confused why only raising 60 degrees Kelvin was, or 60 Kelvin was, if that was good enough or not. And so we actually took it back to Fahrenheit and found out that initially, taking everything back to Fahrenheit, 300 Kelvin is roughly 80 degrees Fahrenheit. So when we put it through the rocket stove, we actually found out that increasing that by 60 Kelvin was actually increasing it by about 100 degrees Fahrenheit. So this is why you would hear, as we mentioned before, about rocket stoves, you're going to hear it buzzing due to the velocity, but it also increases the heat exponentially. And so we found out that even though you may lose heat through the system very rapidly, you still are at a higher heat exiting than when you first put it together. Thank you for watching.